Oh yeah, hi. So anyway, we are continuing on our derivation. So you may or may not have noticed that I have made a careless mistake here. There should be a 2 in front of this term. So yeah, put the 2 in front of it and make corrections on the way down. So let's see what this results in. You can see that when we multiply or divide all these things throughout by 2mn, or we separate the terms out at least, we take note that this is actually equals to this based on the kinetic energy and momentum relations. So again, I'll put the 2 in front of this term here, and this term is just a minus as described here. So to simplify, we find that the final kinetic energy of the iron nucleus is equals to 2 times Pni into Pfef over 2mn, or it's just this if we cover the 2's up, and we minus this term over here. So now where do we go from here? Maybe we want to substitute the momentum relation here so that we can single out how Pni and Pfef are related. So we move on by substituting this in. Again, we substitute this with the p squared over 2m relation, and we obtain the following result. So once this is done, all we need to do is just to collect the terms on one side and factor out Pfef. So this is what is done here. We just move this term to the right hand side, and we find that there's a common factor, which is the momentum of the iron nucleus after collision. So we factor that out, and we find that we arrive at two solutions. One is that Pfef equals to 0, and the other is that this lot here will be equal to 0. Excuse me. So this is the first case, and this is the second case. All right. So what does the first case correspond to? The first case corresponds to basically the iron nucleus being stationary, and the neutron is basically undeflected. So if the neutron is not deflected, this one refers to the angle of deflection being 0 degrees. So the only other case where this head-on collision is possible is that theta equals to 180 degrees, because we are assuming that there's no momentum in the y direction. So in the x direction, okay, so we look at this diagram. In the x direction, there's momentum transfer. In the y direction, there's no momentum transfer. So theta equals to 0 or 180 degrees C. 180 degrees, excuse me. So what about if it's the 180 degrees case? We continue simplifying the expression. Okay, so let's multiply throughout by 2, and we bring the Pfef terms to the right hand side. Okay, so that's all we are doing over here. That's all we are doing there, nothing more. So we want to make P and I the subject, so we can actually bring either the 2 over, or we're not making P and I the subject. We multiply across by mn, and that's what we are doing. Then we make Pfef the subject. So the final expression is as follows: Pfef equals 2 over nn over mfe plus 1, because this is equals to 1 when we multiply this over. So again, we multiply mfe to the top and bottom to simplify the mathematical expression. Then we arrive at this expression here. Now, is this enough to dislodge our atom or displace our atom? we'll need to plug in some numbers to find out. You need to remember that the energy of displacement, or the displacement energy for the iron atom, is about 25 to 35 electron volts. So this is the minimum energy that we must transfer to our iron atom or iron nucleus in order to cause it to be displaced. So just to recap, the first case is where theta equals to 0, and the second case is where theta equals to 180 degrees. And we are calculating for this second case. So the first case is where the neutron is not deflected. Second case is where the neutron is deflected backwards. So in the next video, we'll discuss whether the neutron is capable of dislodging or displacing this iron atom, and we'll be doing that by calculating how much kinetic energy this iron atom will possess in the maximum case. Thanks for watching.